Hello everyone, welcome to the second tutorial for ECE 351. This week we are going to talk about examples of converting a regular expression to NFA, then to a deterministic finite automaton, and then how to reduce this deterministic finite automaton. In your class notes, this is sections 3.4 all the way to section 3.10 from pages 34 to 40. So I think the professor covered a few examples on his lecture on Monday, and we will cover a few more examples now. Okay, so let's get started. So first regular expression we have is f question mark g star. So this regular expression has the language that has the single string f, or the string fg, fgg, and if any number of g's, right? Or even just g, the empty string, and so on. What it cannot have is g followed by an f, right? It has to end with a g. So this is not there. All of this is an element of f g star. Okay. So in the lab manual, this regular expression is converted into an NFA in a peculiar way. This is to demonstrate one issue that you might face when you convert, you finally determinize this DFA, determinize the NFA. Okay, so there are many ways of converting this regular expression to NFAs. One thing you might think of is that you can just have one state, you take this as input, you take f, since you can have 0 or more f's, you can go into the next state with just one f or no f. And then for the next state, you have any number of g's. So the final accepting state can be 1g or any number of g's. In fact, it can also be 0 g's. So this is one way to convert this regular expression to an NFA. But the class notes give you a different way to convert it. And I'm going to stick with that way. I'm not saying that this way is wrong. No, this NFA represents this regular expression. But this example was to point to a specific issue that you will face when minimizing DFAs. So let's stick with the NFA that is given in the notes. That NFA looks a little bit like this. First have state 1. Then just like earlier, you go to state 2. And from state 2, you go to state 3. You can go to state 3 without placing an F. Then you go to state 4 with the G. And of course, you can go to state 4, which is accepting state without a G as well. And this represents an infinitely many G's. Okay, so this you can look at the NFA and convince yourself that this NFA has the language f question mark G star. Right? It can take one f. Just draw that using it can take one f. So that would be going through here, epsilon transition, take another epsilon transition. Okay, it can take 0 f's. So it can accept the empty string, for example. It can take 0 f's. Can take 0 f's to 3, and then an empty string to 4. So it accepts the regular, the empty string. What else? It can have 0 f's and then many g's, right? Okay, so just convince yourself that even though this is not the standard way to convert regular expressions to NFA, this NFA in fact accepts has the language the same as the regular expression. Okay, so let's try to determinize this regular expression, this NFA. Okay, how would you do that? So you first start with the starting state, and we do a subset construction. The first step in the subset construction is to look at the starting state and draw corresponding starting state here. Now, our starting state is going to be equivalent to a set of states of the NFA, and the set of states is going to be the starting state as well as all the states that can be reached from the starting state by epsilon transitions. So in this case, you can take epsilon transition to state 3, and then from 3 to 4, and then 4 to 3 again, right? So the starting state for our DFA is going to be 1, 3, 4. Again, this is a single state. Its label is different. Its label is the set 1, 3, 4. In the NFA, your labels were just numbers. Here, the labels are slightly different. So label does not affect the language that the DFA or the NFA accepts. So we can choose any label that we want. Okay, so you have 1, 3, 4. And how would we proceed now? Now we look at what transitions are possible from this state. First of all, is this an accepting state? Yes, because state number 4 is an accepting state. In the subset construction, a state is accepting if one of its NFA states is accepting. Okay, so now what happens at 4? So at 4, what happens if you're in this state and you receive F? You can, from 1, you can go to 2, which from 2, there is an epsilon transition to 3, and from 3, there is an epsilon transition to 4. So if you get an F, oops, if you get an F from this state, you will get to a state where you have 2, 3, and 4. Again, this is also an accepting state because 4 is an accepting state. Let me just make more space. Okay, do that. Okay. Now, what else are the transitions possible? What happens if you take a G from our state here? So G from 1 does not take you anywhere. G from 3 takes you to 4. And if you're at 4, you can take an epsilon transition back to 3. So if you take a G from 1, 3, 4, you get to a state where you have 3 and 4. So from 3, you get to 4, and from 4, you get back to 3. And that's it. So you have the state 3, 4. Okay, this is also an accepting state because because 4 is an accepting state. Okay, so these are all the transitions from this particular state, now DFA. Now let's look at this state. So from 2, 3, 4, what happens if you take an F? Well, nothing happens because from 2, you don't have any transitions on F. From 3, you don't have any transitions on F. On 4, nothing. So nothing happens if you take 2, 3, 4. What happens if you take if you have a G? From 3, you can get into 4 through G. Then from 4, an epsilon transition back to 3. Right. So from 2, 3, 4, if you take a G, you get this. You get to the state 3, 4. Okay. So now we are done with these 2 states. Now finally, the only states that is left is the state 3, 4. The state. Again, let's look at what happens if you take. So let me just erase this so that it's clear. Okay. Yeah. What happens if you take an F from 3 or 4? you don't declare any we don't have any transitions, so nothing happens. And if you take a G, then if you are at 3, you get to 4, and then an epsilon transition back to 3. So you're right back at the same state. Okay, so now you have an deterministic finite automata. It has 3 states, and all its states are accepted. So now you can convince yourself that this is indeed the correct automata. So let's try to do that. So does it accept the empty string? Well, yes, because the initial state is an accepting state. Good. The next thing is that does it accept just the F transition? Sorry, just the F string. Well, yes, because you get to the initial state, you take an F, and you get to a transition. Then you get to a final state. So it accepts F, and then F followed by any number of G's. Is this valid? Well, it looks like it, because you get to F, then you take a G, and then any number of G's here. So yes, it does accept this. Does it reject this particular string? Yes, because you start from this state, you take a G, and then you don't have any F transitions. So it does correctly reject the state. Okay, so you can convince yourself that this DFA is indeed right. That is, it has the same language as our NFA, which has the same language as our regex. But it has 3 states. Let's try to minimize those states. And this is where the interesting part is in this example. So the first step in reduction is to merge together all accepting states and merge together all non-accepting states. In our example, we just have accepting states. We don't have any non-accepting states. So let me just name them. So let's call this guy A, this guy B, this guy C. And what we have is A, B, C. B, C is an accepting state. And no matter what you do, you will get these 2 transitions, right? Because from A, if you take, from A, if you take an F, you get to B, and then G kind of connects everything. So if you take A, you get to C, from B to C, and from C to itself. So that means that if you apply our reduction algorithm, this is what you're going to get. There is no need to split it because all states are accepted. But this seems wrong, right? In particular, it looks like you can accept all sorts of weird things with this minimized DFA. So this, our minimized DFA is going to accept such a string, but our unminimized DFA, which we thought was right, does not, it does not accept this string. And that behavior is correct. We should not accept this string, but somehow when we minimized it, we went wrong. Okay. And we went wrong because we forgot the error state. So let me just make that explicit. Duplicate this. Okay, so we have our DFA. Any of these other transitions. Okay. Let's take the state B, for example. On G, it goes to C, but what happens on F? On F, it implicitly rejects it. So let's draw a sync state. And on F, B transitions to the sync state. Similarly, on F, C also transitions to this implicit reject state. Okay, and this state on all inputs, it's a sync state, so it's a non-accepting state, and on all inputs, once you reach that state, you're not going to leave that state. Okay, so this is the DFA we have with an explicit error state, which is this guy over here. It is the explicit error state or sync state. How is that useful? It is useful because now when you try to minimize it, so let's again try to minimize it. We have the same strategy. So we merge all the accepting state and the non-accepting states. So earlier we did not have any non-accepting states, but now we made that explicit. So we have an explicit non-accepting state. And we saw, just like earlier, all transitions from F and G, all transitions on F or G takes us back to the accepting states itself. But now we have an ambiguity because on F, B takes you to X, and on F, A takes you to B. So we will have to add a transition that says on F, you go to X, right? Because B goes to X on F. And similarly, so does G, so does C, okay? And on X, you have FG. Okay. Now, adding this explicit error state gives us, tells us what is wrong with our minimization. Earlier, we did not have any ambiguity. All states were combined together, and no matter what input it received, it went to the same state. So it accepted all these spurious strings that we did not want it to accept. But now when you minimized it with the error state explicit, now you know that there is an ambiguity. In particular, you know that if you take F, you can go into the same state or you can go to a sync state. Okay, now let's remove the ambiguity as we normally do. Let's split. So how do we split? How do you determine where to split? Well, I determine it by looking at the inputs. So if I look at A and so the ambiguity is with this particular word F. So A on F goes to B, whereas C and B on F goes to X. So that indicates to me that B and C should be together and A should be separate from them to remove the ambiguity. Okay. So let's try that. We have A and we have B and C. And we know that both these go to X on F, and X does not change. What happens to A? On F, it goes to B, and on G, A goes to C. So G, A goes to C. And what does BC do? So BC on F, it goes to the error state that we have already marked. And on G, B goes to C and C goes to C. So on G, you have this. Okay, now this looks much better. We have minimized the deterministic finite automata from 3 states and an error state. We have went down to 2 states and an error state. And of course, this is an accepting state because both of them are accepting states, because in our deterministic finite automata, all 3 states are accepting. So let's see, let's just make sure that it is correct. So we check whether it accepts the empty string. It does, because it's going to make all error. Okay, it's going to change color so that it's easier. Does it accept the epsilon string? Yes, because A is accepting. A is accepting. Does it accept just F? Well, yes. Does it accept FG? F, G, G, G. It does accept all of this. Does it reject GF? Well, we can see that. So you can take G and then you take F to exit to the sync state. When you draw the minimized automata, you have to get rid of the error state. You have to get rid of the sync state. Let's duplicate this. So once we have convinced yourself that this deterministic finite automaton is correct, we can remove this error state, and this will be a final minimized automata. Okay. If, from A, if you take F or G, you go to BC, and then on BC, if you take G, you just stay there. If it's an F, you reject it implicitly. So that was our first example. What we saw is we started with a very simple regular expression. We kind of put a few strings to make sure that we understand the language well. And then we saw two different ways of converting that to an NFA. One was following the algorithm that we have learned so far in the course. And the other thing was a different algorithm. You can do either of these NFA transformations. Both are correct because both these NFAs accept the same language. So they are equivalent. But we chose to go with the second one because we wanted to demonstrate a particular issue that we will face during DFA minimization. Okay, and we chose the second NFA, and then we did conversion from NFA to a DFA. It had three states, and all of them were accepting. Once we did the DFA transformation, we paused and we made sure that the DFA accepted the same language as the NFA. Once we were sure of that, we said, okay, we can try to minimize this DFA. And then we minimized the DFA without using an explicit error state. And that led us to a bogus DFA. It had just one state and it accepted almost all strings. And when we tried out a few strings, we understood that this DFA has a different language than the unminimized DFA. So we went back, we added back the explicit error state, and we minimized the DFA again. And once we minimized it again, we once again checked whether the DFA accepts the same set of strings. And this check is not a proof. This is just you look at a few strings, a few accept strings, a few reject strings, and make sure that it kind of makes sense. You accept everything that you expect to accept, and you reject everything that you expect to reject. Once we made sure that the DFA was correct, we can remove the error state, and this is the final DFA that you get. Okay, cool. For this tutorial, we have one more example of Regex-NFA-DFA and minimization example. And that is in, I believe, section 3.10. And the regular expression there is either dB or FM, the whole star. Okay. Okay, so I don't even have to write down the strings for this regular expression. You know what it's going to be, right? So it's like dB, FM, dB, dB, FM. It's just an infinite repetition. Okay. How would you draw the NFA for it? You first draw accepting a state. Now I'm going to draw the OR condition. So the OR condition can be that, forgot to number them, 1, 2, 3, D, B, 4, 5, 6. And if you reach 6, you automatically accept. Otherwise, you can go back on an epsilon transition. And then you can have either F or M. And of course, since it's a star, you can have an epsilon transition here. Okay, so I just started with an initial state. I said I had to split on this particular OR. So I draw a state for, in order to make the split. And I draw two epsilon transitions, one for the dB branch and one for the FM branch. And I merge it at state 6. And then since it's a star, you can come back and repeat this as many times as you want. Also, because it's a star, you can go from you can also accept the empty string. So you have to have a transition from 1 to 7. So that is our NFA. Let's try to convert that to a DFA. What would our initial state be? So let's just call it P. I think the nodes also call it P. It would be the set of states that can be reached from the first state. So state 1 can be reached from the first state, and then look at all the epsilon transitions from 1. So there is 2, there is 7, and from 2 you can have 3, 8. Okay, so I think that's it. Yeah. So 1, 2, 3, 8. 1, 2, 7, 3, 8. Okay, so that's our first state, and it's an accepting state because 7 is an accepting state. Now, you have D, B, F, and M. Okay, should probably make this smaller because it's going to be a big DFA. So let's do that. E 1, 7, 2, 3, and 8. Okay. And next state is going to be what happens on D. On D, there is only one transition. So from 3, you can go to 4 and nothing else. No other arrow has D as its label. So if you take D, then you reach a state Q that only contains, it's a singleton set. It says 4. It's not an accepting state because 4 is not an accepting state. And from 4, if you take before that, we can do this thing. F, E, Q, R, and this is just 9, right? Because from 8, if you take F, you get to 9, but there is no other transition from any other state on F. So, okay, we started with the initial state. We took both strings D and F. And what about B and M? Well, B and M is going to give us an explicit error state. So we saw it's a good practice to draw this explicit error state from the previous example. So let's just draw it here. So on B and M, you go to this error state because there is no transition on B and M from any of these states. Okay, so now we are done with this state. Let's go to state Q. On state Q, you have 4, and 4 on B goes to 5. And 5 takes an epsilon transition to 6, which takes an epsilon transition to 7, as well as 2. And 2 takes you to 3 and 8. Okay, so now you have a big state, which includes 5, 6, 7, 2, 3, 8. Ouch, I'm short on space. What can you do about that? Once again, from 4, you can take a B to 5. But from 5, you can take an epsilon to 6. From 6, you can take an epsilon to 7, back to 2. And from 2, you can take an epsilon to 3 and 8. So you have 5, 6, 7, 2, 3, 8. 5, 6, 7, 2, 3, 8. Okay, and it's an accepting state because 7 is an accepting state. Okay, so that's all the transitions from 4. So again, we have made the error state explicit. So let's just make it explicit. From Q, all other letters take you to the error state. So you have D, F, M, Yeah, those are the three things. They all take you to our error state. Now let's try something. Let's try the next transition, that is from state 9. Again, this is also almost going to be the same as, sorry, what happened here? Yeah, there is a slight asymmetry here, but I think it's okay. Anyway, so from state 9, you can take a transition to 6, and that will take you back to 7 and 2 and 3 and 8. So it should be 6, 7, 2, 3, 8. T 6, 7, 2, 3, 8. Okay. So again, this is an accepting state because 7 is an accepting state, and you make this transition on M. Okay. And of course, we're making the error state explicit. So anything that is not M, just D, F, and B, you go to an error state. Okay. And finally, we have just two more states, S and T. And S is 5, 6, 7, 2, 3, 8. And let's see what happens on D. So since we have, let me just erase all the red lines because they are confusing. There's an epsilon there. Okay. So let's go on S. Let's see what happens. So if you take a D, so S has got the state 3. So D is going to take you to 4. Okay, so you're going to come back to 4 on D. No other transition on D because there is no other label on this DFA with D, with NFA with D. And then what about F? Because you have state 8, F is going to take you back to 9. So 9 is our R. Okay. And what else is there? Is there any transitions from 5? No, 5 is just an epsilon to 6. 6 is just an epsilon to 7 and an epsilon to 2. 7 is just nothing, it's just an accepting state. Then 2 is again 2 epsilons, and 3 and 8 we have already dealt with. So everything else other than D and F is going to take you to an error state. And this is getting crowded here. So this is BM. And then you have state T. And I think with the same reasoning, if you do F, you get back to R. And with T, you get back to Q, I guess. Right, so because you have almost the same states. And on everything else, which is B and M, you get to the explicit error state. Okay. Now, this is a little bit messy, so I'm just going to redraw this with just P, Q, R, S, and T. Okay. Let's see here, P, Q, R, S, T. So from P, you can take a D here, and then Q, you can take a B here. F and M, and then you get back on D, you get back on F, you get back on F. Oh, it's again getting messy. F, and then D, get back on D. Oh no. Okay. And what were the accepting states? I think S was an accepting state and P was an accepting state. And the initial state was also an accepting state. Okay, so this is the same automata you have. Hopefully, this is clearer to read. But one thing I have missed is the error state. So you have BM to the sync or the error state. And then you have from Q, you have anything other than B to the error state. So that is DFM. On R, anything other than M, which is D, F, and B. And S and T, you have from S, anything other than D, F, so BM. Similarly, T, BM is going to an error state. Okay, so now this should make sense, even though the drawing is ugly. So if you take a D, then you can only take a B. On all other transitions, you go to an error state. So that kind of makes sense because our language was DBFM star. And similarly, if you take an F and you take an M, if you take an F, then everything other than an M will take you to an error state. That is good. And then if you take an F and an M, then you get to reset. If you see an F, you go back to R, or if you see a D, you take this transition back to Q. And then you can either wait for a B or an M, which makes sense. And then it's an infinite loop. Of course, it accepts the empty string because the initial state is an accepting state. It accepts DB because you go from P to Q to S. Similarly, FM accepts these three things. What it does not accept is DF, for example. Does not accept DBF and then a D. Does not accept this, does not accept this. So we kind of have a sanity check to make sure that our conversion from an NFA to a DFA is correct. Now let's try to minimize this. This looks ugly, but if you have the intuition, it's the ugliness, you can gloss over the ugliness. So you have P, S, and T. These are the accepting states. And then you have Q and R as the non-accepting states. Let me just draw this somewhere clean. Q and R are the non-accepting states, and obviously you have X. I'm going to draw the error state explicit because most definitely we are going to have to split it and remove it. Okay. Okay, so PST is the start state, and from PST, what all can happen? So from P, you can take a D to Q and an F to R. So D or F, so D, F to QR. And what else? From S, you can take a D to back to Q and F to R. We already recorded that. Similarly, T, you can take a D or an F to back to QR. We already recorded that. So we are done with this state, except now you have got the error state. So to the error, you have BM and BM from T and BM from S. Okay, so this looks good because you all three states agree on how to go to the error state as well as the states QR. So hopefully we won't have to split the PST state. Now let's look at the QR state. Oh, this is MS. From QR, you can take a B to S and M to T. So let me just draw that here. VM EM. Okay. Basically, that is the only legit outgoing transition. So from Q, you only have one transition to S, and from R, you only have one transition to T. Everything else goes to the error state, right? So DFB and DFM. Okay, so let's draw that. DFBM. Okay, so this is our whole minimized DFA, but it has got ambiguity. In particular, you have the problem with M and B. So M and B from QR state goes to PST or the reject. And so let's look at that. What happens? From R, if you take M, you get to T. But if you take M from Q, you get to a reject state. Similarly, if you take a B from Q, you get to an accepting state. But if you take a B from R, you get to an error state. Okay, so no other option but to split it. So PST, accept this. You have split Q and R. I'm just going to make X here. So maybe that's easier. So let's see here. What happens on D? I think you go to state Q because P on D goes to Q and S on D goes to Q as well. Similarly, T on F goes to R. Similarly, P on F goes to R. So go like this, and then B and M. So you can just fill it from memory, or you can just fill it from your intuition of what the regular expression is. So it has to accept D and B or F and M, right? So now this is FM star and this is DB star. Okay. Sorry, the one on top is DB star and the one on bottom is FM star. And everything else is is going to get rejected. In particular, we have M, D, F is going to get rejected. D, F, and B are going to get rejected. Okay, so let's just make that clean. We don't care about the error state. Make this better. Okay. Okay, so this is our minimized DFA. It has no ambiguous transitions and it accepts everything that we want. So just again, it's always good to do a sanity check. So first I'm going to check whether it accepts the empty string. It does, which is good. Then DB, yes. DBFM, yes. But if I confuse this thing, DF and BM, then it's not going to accept it because on D you get to Q, there is no transition on F, so you fail. So this is our minimized DFA. Okay, so this example was a bit more involved. We started off by saying that here is a very simple regular expression, DB or FM repeated infinitely many times. We drew the NFA corresponding to it, and the NFA had too many states. When you draw the DFA, on paper it looks complicated, but in reality it's very easy. Then we made it a point to mark the error state explicitly. So when we converted, when we tried to minimize the DFA, it helped us. Unlike the earlier example, we did not go to a bad DFA in the first try. Then we minimize the DFA, and then we made sure to test it on many strings in our head to make sure that our conversion is right. Okay, so that's it for this week's tutorial. Thank you for listening.